All right, guys, let's do this review. Number one is dealing with an exponential function. So here's all the things that we have to find, even with the extra little x-intercept, now that we have those skills to be able to do that. So starting with, if you know we have an exponential function, you know the parent graph, again, is going to look like this. It's a growth function. It goes through 0, 1, so I know the domain is going to be all real numbers. Also, notice with this one, and it's not being asked necessarily right here with what I have listed, but we have to know the transformations on this. So if I took this equation, I'm just going to set it equal to y now. This would be 3 to the negative. If you pull that x or that negative out, that's going to be x minus 2. So a couple things you have to be aware of on this function before I start doing everything else is that this negative right here is going to be a reflection. So I'm going to say reflect over the y-axis, because that negative is inside the function, so it's a reflection over the y-axis. This minus 2 is inside the function, so that's your h value, so we're going right 2. So once you know all that and you understand because of this 3, that's what makes it a growth curve, then we can start really doing everything here. Now, I could put all this in here right now, but what I'll do is I'm going to take this and put it in my graph. So if you're looking down here, you normally have a point at 0, 1, but that point's going to go right 2. So we're going to go right 1, 2. So I now have a point at 2, 1. So I have a point here. So that's the original point that I had. And then I'm going to reflect over the y-axis. So I know my graph's going to be going down. But I do know because of that, because of the fact that there's no vertical shift, I know that I'm going to be decaying and not growing because I've taken this graph and I reflected it over the y-axis. So your range is still going to be from 0 to infinity. You're not touching it because of your horizontal asymptote. Therefore, your horizontal asymptote's at y equals 0. It hasn't changed. The x-intercept, because I have a horizontal asymptote here, there's none. So you can still find that. That's not so bad. The y-intercept we need to find. So I'm going to do that right here. And again, the y-intercept is always going to be 0, comma, and then some number. So I'm going to take this equation, plug in 0. So this is going to be 3 to the negative 0, so 0 plus 2. So that becomes 3 squared, which is 9. So your y-intercept is at 0, 9. So putting it up here, I'll just kind of put a point right there. I'll call it 0, 9, just because I'd run out of room otherwise. So again, that's where you're going to kind of put that point. I've found everything other than my end behavior, which I'll do here in just a second, but this is going down. It's decay because of that reflection. My concavity is not very good right here, and I'm not going to erase it. So it's going to come down here, touch this point, and it should level off. And again, that graph is probably not the best. Maybe I'd be more like this, but I can't really erase very well here. So that's a general sketch of your graph. Now your end behavior, as you're going to negative infinity, this one's going up, so you're going to infinity. As you're going to the right, it's approaching 0. So that's going to be your graph and all your information for number 1. Next up, we have number 2. This one has 2 parts. We're basically just evaluating here. And both of these are being set up, like for this one, just set it equal to y. This is one where you have to kind of get your bases to be the same because we're going to have an exponential equation. So we're going to go 3 to the y equals 1 over 81. So the key is really to make that 1 over 81 something that is a base of 3. So I start by making this 81 to the negative 1, and then we start breaking down the 81. So that's 9 times 9, and that's 3 times 3, 3 times 3. So as you come up here, we have 3 to the y equals 3, and notice there's 1, 2, 3, 4 of those. So that's 3 to the 4th. Therefore, y is equal to 4, which is what your log is in this one. So that's A. If you look at B, same thing here. Set that equal. I'll make this an x this time just so it's a different variable, but this is going to be 32 to the x equals 2. Now, in terms of this one, you want to make the exponents or the bases the same. I'm going to have to, once I do that, set the exponents equal. So I'm going to make that an exponent of 1. So when I break this 32 down and I set my exponents equal, I'm going to set that one equal to 1 over here. So the 32, that's going to be, again, 16 times 2. 16 is 4 times 4, and that's 2 times 2 times 2 times 2. So I have 1, 2, 3, 4, 5 2's that make up 32. So this is 2 to the 5th raised to the x equals 2 to the 1st. And let's bring that down. So this is going to be 2 to the 5x, and that's going to equal 2 to the 1st. Therefore, 5x equals 1. So x is going to be 1/5. So that's going to be the second one for B, or number 2, I mean. Next up we have, again, number 3, we are condensing logarithms. So there's a lot going on this one, as you can probably see. I'm just going to go ahead and start here, and I'll work my way over. I'll just kind of do everything one at a time. So to get started, I'm just going to go ahead and move this up to the top. I'm going to try to do 2 steps at once just because of my spacing here. So this is going to be m squared and n to the 6, but I'm going to write it as 1 log. So this is going to be log base 4, and I'm going to multiply these 2 inputs because I'm adding. So this will be log base 4 of m squared times n to the 6th. So that's going to be those 2 logs combined. I just use the power rule and the product rule together. This one I'm going to distribute that 3. So it's going to be minus parentheses log base 4. Now what I'm doing is I'm taking this 3 and I'm doing 2 steps again. So follow me here. When you distribute, you have a 3 in here. So what I'm then going to do is I'm going to take that 3 and I'm going to move it into my exponent. So it's heading up there. So this is now going to be 3 to the 3rd. So that's 3 times 3 is 9. 9 times 3 is 27. So this is log base 4 of 27 plus log base 4 of j cubed. So now I end up with log base 4 of m squared into the 6th minus, and I'm going to combine these, so this would be log base 4 of 27 j cubed. So now we have these 2 logs, they're being subtracted, so when you write this as 1 log, this is log base 4, and then I'm going to now have a fraction, okay? So this is going to be m squared into the 6th on top. That's my first input. Here's my second input, and I'm dividing those 2 inputs. So this divided by this, so that's going to be over 27 j cubed, and that is your condensed logarithm. So that's going to be your answer. There's nothing else to do there. So that's number 3A. 3B, I just have a 1 out here. That doesn't really do too much. I do have these logarithms that I want to combine. So on B, I'm just going to take these and combine them. So I'm going to still have a 1 out front, and then plus, and it's going to be natural log of, and before I do that, sorry, I forgot the 4 here. That's going to be x to the 4th. So this is going to be natural log of 3 divided by x to the 4th. And again, there's not much else you can do because you just have that 1 right there. It doesn't really do much. So that's going to be your answer for B. So that's 3B. Moving on to number 4. This one's asking us to solve an exponential equation. So again, the key on this is to get, just like we had over here, to get the bases to be the same. So I'm going to look at this right-hand side and think of that as 3 times 3. So I'm going to have 3 to the x plus 8 equals 3 squared raised to the 2x. So this is 3 to the x plus 8 equals 3 to the 4x. So I have the bases the same, so now I can use the 1-to-1 rule, and I can set the exponents equal to each other. So x plus 8 equals 4x. So when you solve this, I'm going to subtract x from both sides, so I'm going to get 8 equals 3x, divide by 3, and here we get x equals 8/3, and that's going to be your answer for number 4. So finally, number 5, we're solving a log equation. So in this case, we are going to want to condense the logarithms. So I'm going to combine these 2 right here. So that's going to be log and I'm going to multiply these. So I'm going to have x times x minus 3. So that's, again, my input for my log. That's equal to 1. So once you condense the logs, you can then write it as an exponent. So this is log base 10, so that's a 10 right here. So it's going to be 10 to the first equals this. So I'm just going to write that as 10 because that's what 10 to the first is. And that equals x squared minus 3x. I'm multiplying that out because this is just going to be a quadratic equation. So I'm going to set it equal to 0, and I'm going to factor it. So I have 0 equals, and now I have x squared minus 3x minus 10. Using product sum here, we're going to just see we have x times x. 5 times 2 is going to multiply to give you 10, and negative 5 plus 2 adds up to negative 3. So my answers that I have right now are x equals 5 and x equals negative 2. Now again, on logarithms, because the domain's restricted, we need to make sure we're checking for extraneous solutions. I can tell right away negative 2 is going to give me an undefined answer. So x equals negative 2 does not work because I'd have log of negative 2. This would also be a negative, so it doesn't matter. Whereas 5, if you plug that in, it will work. So this will be your answer, and that is your only answer. This is extraneous. We don't include it. So that's going to be number 5. All right, now number 6, we're condensing logs again. So here we are subtracting, which means we're going to divide our inputs. So this is going to be log base 2 of x divided by x minus 4 equals 5. So here we have a condensed log, so we're going to write it as an exponent. So this is going to be 2 to the 5th. We're going to take this, raise it to that power, set it equal to that. So this is going to be 2 to the 5th power equals x over x minus 4. So this one you can just basically deal with like it's a proportion. This is going to be 32 over 1 equals x over x minus 4. So I'm going to cross product here. So I'm going to multiply the x and the 1. So that's just x. And I'm going to multiply the 32 and the x minus 4. So this is going to be 32 x minus 4 equals x. I'm going to bring that up here and keep going. So that's going to be 32x minus, let's see, it's 128. And that's going to equal x. And this is a linear equation. So that means I can just go ahead, I'm going to move the 128 to this side by adding it. I'm going to move the x over here by subtracting. So that's going to give me 31x equals 128. And don't think we can really simplify that. Almost positive here, but at least I can give you a decimal answer as a possibility. So that's fine as well. So this is going to be obviously x equals 128 divided by 31, which is approximately, if you do the decimal version, 4.129. So those are your two answers that you can get. So that's going to be number 6. Now I have number 9 right here because of the space. I'm going to move on to number 7. So 7 is basically graphing. So we have our logarithm, and they want us to find a few different things here. So starting with the transformations. Let's make sure we understand what transformations we have. First off, this 2 tells me the parent graph. It tells me it's going to look like this, as opposed to like a base being 1/2 and being flipped over the x-axis. So that just tells us a parent graph. And this 3 is a vertical stretch because this is not in parentheses. So like that x is by itself inside the log. So this is going to be up 3. So those are our transformations. Because we're taking this graph, we're going up 3. It doesn't change our domain because it's just this graph shifted. So the x values don't really change in terms of the domain. So the domain would be 0 to infinity. That's an ugly infinity, but that's an infinity. The range, again, it still goes up and down forever, so that's still going to be all real numbers. Now the x-intercept will be affected. So I do need to find that, but I do not have a y-intercept because I still have a vertical asymptote here. Again, I've taken this graph, I just moved it up. So anyway, my y-intercept is still none because I have my vertical asymptote there. By the way, I have a vertical asymptote at 0. So that's going to be that piece. And again, to find the x-intercept, we need to go ahead and realize that it's x comma 0. So our y value is going to be 0 when you're on the x-axis. So that means I'm going to take this equation and I'm going to call my y value 0. So it's going to be 0. Now I actually write it, I'll flip the equation when I do it. So it's log base 2 of x plus 3 equals 0. I just kind of flip-flopped it because we're used to seeing it this way. So anyway, before you rewrite this as an exponent, we need to take this 3. We need to isolate that log. So I'm going to move it over here. So we have log base 2 of x equals negative 3. So I'm going to go 2 to the negative 3 equals x. Well, that's 1 over 2 cubed, which is 1/8 equals x. So your x-intercept is going to be at 1 over 8. So that's your x-intercept, which makes sense. You've taken this graph and shifted it up, so it's just getting closer and closer to that 0 value. So if I take my graph, I'm going to be right here at about 1/8, 0. I have a vertical asymptote at the y-axis, and here's my graph. Again, it's just shifted up 3. So the point that we would normally have at 1, 0, well, it's been moved up 3. So I'm going to go up 1, 2, 3, up 1, 3 is going to be right there. So I have that point, and then I just go ahead and draw my graph. So it's going to come up through this point at 1/8, start to curve off to the right, and there is your log graph. So that's the graph, and again, anything else we have left to find, we can hopefully find here. The end behavior, as x goes to negative infinity, well, that's not going to actually approach negative infinity, so let me fix that. It's actually approaching, in this case, 0. So it's going to approach 0. As x approaches 0, you're going down forever, so that's negative infinity. And again, be aware this graph is actually approaching the asymptote. I have it kind of curving back. We don't want it to do that. Just be careful with it. As I go to the right, I am going right forever. And as I go right forever, I'm going to be going up to infinity. So that's your end behavior for number 7. Moving on to number 8. So on this one, we have a rational function. So in this case, I kind of want to see like my x-intercepts, my y-intercepts, my asymptotes. I got to find all this information. I'll go ahead and do this last because we don't really have much of a parent graph to really look at here. So to start off with, let's go ahead and do our x-intercept. So the x-intercept, what we have to do is take this function. I'm just going to go ahead and move it up here, use the space that I have, and I'm going to factor it. So I'm going to write the two factors here. I have x, x. I want to get a product of 20 with a sum of 9, so that's going to be 5 and 4, and you just add these together. So those are your factors. So your denominator is going to be x minus 4. So now you have all your factors. So to find your x-intercepts, we set in this case, the numerator equal to 0. So you're going to get 2 x-intercepts. So those 2 x-intercepts are based off of these 2 factors in your numerator, because if the numerator is 0, the entire function is 0. So in this case, we have negative 5, 0 for the first factor, and negative 4, 0 for the second factor. So those are going to be your 2 x-intercepts. The y-intercept is where you plug in 0 for x, so you're going to always have 0 comma y. So I'm going to plug in 0, and you're going to get 20 over negative 4. So 20 divided by negative 4 is going to be negative 5. And again, that's just me plugging in 0 for x. Notice no factors cancel, so there are no holes. Next up, our vertical asymptote. That's when your denominator, the non-canceled factors, are set equal to 0. So in this case, x minus 4, that's my denominator, and it's not canceling with anything. So my vertical asymptote is going to be when you set x minus 4 equal to 0, so x equals 4 is going to be your vertical asymptote. Next up, we have our horizontal asymptote, which we actually don't have. You'll see the degrees are off here. So there's no horizontal asymptote. However, we are going to have a slant asymptote, and we find a slant asymptote by dividing this function. And so it's going to be y equals, and I'm going to go ahead and find it right up here by dividing this function. I'm going to use synthetic division to do it, and remember the quotient is your slant asymptote. So I'm going to divide by x minus 4. My coefficients for my numerator are 1, 9, and 20. Remember, we're looking for the quotient. So I'm going to pull down the 1. 4 times 1 is 4. 9 times 4 is 13. And again, I don't care about the remainder. It's just the quotient I'm looking for. So I'm going to use that. My slant asymptote is y equals x plus 13. So that's going to be your slant asymptote. So I'm going to go ahead and take all this stuff before I find my domain, my range, and everything, even my end behavior. I need to graph this. So I'm going to take my x-intercept here. I'm going to go to -5. So 1, 2, 3, 4, 5. I got an x-intercept at -5. I also at -4. So those are my two x-intercepts. I have a y-intercept at -5. So there's my y-intercept. So those are my intercepts. My vertical asymptote's at 4, so I'm going to go over to 4. So there is my vertical asymptote. And your slant asymptote is x plus 13. So it's going to be way up here. But I can tell, like if I put a point up there, it's going to not be to scale. If you want to figure out where it touches the x-axis, I'm going to go ahead and do that real quick so I know where it's touching over here. And again, all you're doing, if you want to find out when it touches the x-axis, you plug in 0 for y, and you get x plus 13. So you can see that -13, that's where that asymptote touches. So it's going to be like way over here. And I know I'm not even to scale, but you know, we'll have to live with that. Okay. So I'm running out of room. You're going to see I'm going to have to get creative here with my graph, but I'll make it work. So at this point, I can see what's happening here based off the points that I have. My graph has got to be coming, and again, my scaling's way off here, but I'm going to start down here. I'm coming, and notice this is approaching this asymptote, but it's going to be heading up. It's going to curve in. It's going to touch these 2 points. I know it's touching these 2 points in this direction because it's going to have to come down and touch -5. So I'm going to have it do that. And again, it is approaching. Just you can't see it yet, but it's going to be approaching that vertical asymptote. So this graph is just stretched like crazy. Now, I don't have any points down here. I don't have any x-intercepts. So by default, this little section on the top here, that's why I said I'm going to have to get creative, but this is where my graph is going to be on top. It's going to be approaching those 2 asymptotes, and I know that because there's no points down here. So this is my graph. What you can see, hopefully, at this point, is that the domain is going to be restricted at 1 value, which is going to be at 4. So I'm going to have a domain of -infinity to 4, and it's going to skip over that point and go from 4 to infinity. So that's your domain. Your range, again, I'm not really going to ask too much about the range because we don't know exactly. I mean, I'm just going to guesstimate it. Now, with calculus, you can do derivatives and find the mins and maxes. That would be awesome. Here, it's -infinity, and we don't really know how far up this goes. You can be like approximately 0.5. I'm not going to ask you that, and I'm not going to force you to find it at this point. But up here, I don't, again, without me doing all the extra math to figure out where this goes, I know it's somewhere, I don't know, probably around 16-ish. We don't really know to infinity, but we don't know. This doesn't really matter in this case because we can't find it for sure. I'm just throwing numbers to give you an idea. But there's a gap there, obviously, so I'm just talking about there possibly being one. Lastly, the end behavior. I said I have to get creative on this. So the first one, the limit of f of x as x goes to -infinity. So as I'm going to the left, this is going down. So that would be -infinity. This one, as x approaches positive infinity, as you're going to positive infinity right here, it is going up. So this one's going to be infinity. So that's your end behavior for 8a. So that's, again, obviously number 8. And then lastly, we're going to do 8b. This one is already factored for you, so that's kind of nice. So I'm going to go ahead and find that x and y intercept to start. The x-intercept is when the numerator is equal to 0. Notice nothing cancels, so I'm just going to go ahead and find it. So this is going to be at 6, 0. The y-intercept is when you plug in 0 for x. So this one would be, and just to kind of do the math, it's going to be at 0, comma, and then a number. So that number, when we work it out, is going to be -6 divided by 3 times 5. because I'm plugging in 0 for x, and this is what I get. So that's negative 6 over 15. To get the actual number, I mean, you can tell it's almost negative 0.5. I'm just getting an actual value. Oh yeah, it's negative 0.4. I'll probably figure that out. But anyway, that's going to be your y-intercept. And now your holes, there are none because no factors cancel. So I'll just say none here. Vertical asymptote is where the denominator set equal to 0. So I'm going to say x equals negative 3 and x equals negative 5. So those are going to be my two vertical asymptotes. Now this one, when we do horizontal asymptote, I actually do have a horizontal asymptote. The key here is the degree of the denominator, or degree of the numerator, is less than the degree of the denominator. Now when that occurs, your horizontal asymptote is always going to be y equals 0. So that's going to be your horizontal asymptote for 8b. So with all that information, let's go ahead and plug this in. I do have a horizontal asymptote at 0, so that's going to be my x-axis. I have vertical asymptotes at negative 3 and negative 5. So I'm going to come up here, negative 5, and then negative 3. I have a point. See, I got a point at negative 0.4. So I'm going to put a y-intercept right there, negative 0.4, and an x-intercept at 6. So 1, 2, 3, 4, 5, 6, right there. Okay, so in this case, this is the one where you have to pick a couple test points. I can tell you what's happening as you go off to the right. So you are going to start going down, and then this point is going to sit here and get almost flat right here at negative 0.4. And you'll notice here it has an x-intercept on the horizontal asymptote. All that's telling you is that it's coming up, it's going through that point. I know I got a little off center there, but it's going through that point, and then it's just going to approach that horizontal asymptote from the top side. Again, the horizontal asymptote is just an infinite discontinuity. So as you go off to infinity, that's when it approaches it. So in between there, it can touch, and it will touch the x-axis from time to time. So anyway, that's going to be the part as you go off to the right. Now in here, I don't really know what's happening. I know my graph is either going up or down, or upside, like a parabola looking thing, or an upside down parabola looking thing, but we don't really know for sure. So I got to pick a couple test points. So I'm just going to come over here, make a little XY table. I'm going to pick a couple points and see what we get. So I'll start here in the middle. So 1, 2, 3, I'm going to plug in negative 4, and I'm just going to see if I get a positive number or a negative number. So if I plug in negative 4, that's going to be negative 4 minus 6, so negative 10. Negative 4 plus 3, so negative 1. And negative 4 plus 5, so positive 1. So this gives me, in this case, two negatives on top and bottom, so it gives me a positive 10. And again, really what I'm concerned with is if it's positive or negative. So basically, this is all it's telling me, is it's going to be positive. So it's going to have to be approaching my vertical asymptotes, and it doesn't touch down here. So that's going to be the sketch of my graph in there. Now I'm going to pick a point to the left of my vertical asymptote out here to see if my graph is either going up or down. I don't know which one right now. So I'm going to go 1, 2, 3, 4, 5, negative 6. I'm going to plug that in, and again, I'm just looking to see if I get a positive or a negative number. So if I plug in negative 6, that is negative 6 minus 6, so negative 12. Here I get negative 6 plus 3, so negative 3, times negative 6 plus 5, which is negative 1. So this is now going to be a positive right here. So when you multiply these, you get negative 12 divided by a positive 3. So that's negative 4. So that means I'm down here. So my graph is going to look like this. So there is a sketch of your graph for 8b. Now the last thing, if you look domain and range, my domain, that's negative infinity. I'm going to go all the way up to negative 5. I'm going to skip over that point. Then I'm going from negative 5 to negative 3, skip over that point, and then I go from negative 3 to infinity. Your range, again, notice you are skipping over here, and again, we don't know how far this gap is, so I'm just going to kind of give you a guesstimate, but negative infinity to 0, and we don't know how far, but I know I had like a 10 here right in the middle, so if you think about that as like a symmetric here, it looks like I'm going to get up to 10 inside that point that I found. So I'm just going to go and say and guesstimate from 10 to infinity. So that's going to be your range. And then your end behavior, as you go to negative infinity, as I go up to the left, you'll notice I'm approaching 0. I'm approaching the horizontal asymptote. And that's really what this end behavior is going to be. As I go to the right, I'm also approaching 0 because that is my horizontal asymptote. So remember that when you have a horizontal asymptote, that's really what your end behavior is. It's you approaching that infinite discontinuity. So that's going to be 8b. And lastly, we have number 9. I'm squeezing that on 9a here. Just find the partial fraction decomposition. So on 9, this is going to be case number 1. So remember, we have, in this case, it's going to be a over x minus 2 plus b over x plus 2. So again, we're using case number 1. We have a non-repeating linear factor. So what I want to do is try to get a common denominator in terms of a and b. So this would be x plus 2. This would be multiplied by x minus 2. So I'm going to end up with ax plus 2a plus bx minus 2b. So that is going to be my numerator. Obviously, I'd have that denominator. So this all equals 8. And again, if you want to talk about the x term, that would be 0x plus 8. So my x terms are going to be ax and bx. So I have a plus b equals 0. Here for my constants, I have 2a minus 2b. That's going to equal 8. So if I'm solving this, I would maybe use substitution. I'll say that a is equal to negative b. So I'm going to come down to equation number 2. I'm going to say a, that's negative b. So this is going to be minus 2b minus 2b equals 8. And that's me using this substitution right here. So I'm plugging that in for a. So that's negative 4b equals 8. So b is negative 2. So now that I have b, I know a is just the opposite of that, so a is positive 2. So your final answer, you put this all together, I'm rewriting this, but I'm just plugging in these numbers right here. So this is going to be a, which is 2, over x minus 2, plus negative 2, so minus 2 over x plus 2. So those are your partial fractions. And that is the answer for 9 part A. All right, guys, number 9 is another partial fraction decomp. The one thing you're going to have to notice on this before we start is that the degrees are equal, which means before we can do our decomposition here, actually this is part of the decompositions, we're going to have to do some division. We're going to have to divide these first because the numerator on the top needs to be less than the degree of the numerator on the top. Needs to be less than the degree of the numerator on the bottom. So I'm going to start by doing some quick division, which means I'm going to take this, I'm going to go x squared minus 2x plus 0. I'm dividing that out of 3x squared plus x minus 4. So we're going to say what times x squared is 3x squared, so that's going to be, in this case, 3. And then we're going to say, we're going to go ahead and multiply that, so we're going to get 3x squared. And I'm going to have minus 6x, and then 3 times 0 is 0. So when I divide this, this comes out here. We cancel these first terms. 1 minus the negative 6 is plus 1 plus 6, so 7x. Negative 4 minus 0 is minus 4. So at this point we say what times x squared is negative 4. And again, when you're thinking of that, that's really not going to give you much. Or sorry, because I'm saying negative 4, that's why I was screwed up. Sorry, what times x squared is 7x? And again, same thing's going to happen here. That's because this is our remainder. So what we have is just 3 in our numerator with a remainder of 7x minus 4. So our quotient is 3. So we're going to get 3, which is now plus. And my remainder is 7x minus 4, and that's over x squared minus 2x. So I've broken this up a little bit here. I now have a numerator of 1, denominator of 2. degree of 2, I should say. So now I can do my partial fraction decomposition of this term. So now I'm going to take this, I'm going to factor it so I can see what case I have. And this is going to be case 1. I have 2 non-repeating linear factors. So that means if I come up here, I'm going to have, and I'm just looking at this, remember this 3, it's going to get brought into my final answer, but I'm looking right now as just this case. I'm going to have a over x plus b over x minus 2. So I want to get a common denominator here of x minus 2. So I'm going to multiply this by x minus 2 and this number by x. So I'm going to have ax minus 2a plus bx. That's going to be my new numerator. Now remember that numerator is equal to 7x minus 4. So I'm going to set that equal to 7x minus 4, and that's going to be where I get my equations from. So start with my x terms. I have a plus b equals 7. Those are my x terms. And then I have negative 2a. That's my only constant. That equals negative 4. So I know that a is equal to 2 when you divide these. Therefore, 2 plus 5 is equal to 7. So my final answer, bring in the 3. I have 3 plus 2 over x plus 5 over x minus 2. So that is going to be 9b. So next up, we're going to have our calculators for this. We have log base 3 of 7. So log base 3 of 7, that's just going to be a change of base. So we're just going to go on our calculators, log of 7 divided by log 3. I'm just using the change of base formula. And you use that with natural log 2 if you want. So log 7 divided by log 3 on the calculator is approximately 1.771. So that's going to be 10a. Next up, I have 10b. This one I'm going to want to take the log of both sides. So I have log 11 equals log of 6 to the 3x. So here I'm going to pull that 3x out front. So I'm going to have 3x times log 6 equals log 11. And again, our goal at this point is we're just solving this for x. So I'm going to divide both sides by 3 log 6. Again, doing that on both sides. Remember, we have our calculators. Or if you don't have your calculator, you just write that answer as log 11 over 3 log 6, or log of 6 cubed if you want to multiply that out. But here I'm going to use my calculator. I'm just going to type in that number. Again, I'm typing in this right here. So that's what kind of gets plugged in. So I have log 11 divided by 3 log of 6, or log of 6 cubed. So I'll just do 3 log 6. That's what I have written, but it doesn't really matter. 3 log 6. And you get approximately 0.446. So that is going to be 10b. Okay, next up is C. Here I want to definitely do natural log because my base is e. So I'm going to natural log both sides. So natural log of e to the x plus 1 equals natural log of 6. So now when you have this natural log e, I'm going to take this x plus 1. I'm going to pull it out front. But the natural log of e is 1, so it's going to go away. So you have x plus 1 equals natural log of 6. On your calculator, you're now going to type in x equals, now I'm taking this 1, I'm moving it to the other side. So it's natural log of 6. Be aware that's 6 right there. My thing's dying, I think. Minus 1. So that's what you plug into your calculator. So on your calculator, I'm going to go natural log of 6 minus 1, which I get approximately 0.79, in this case 2. So that's going to be C. So now moving on to D. This one we just go ahead and write it because it's already a natural log, so it's e. So I'm going to go e to the 13 equals x plus 5. I'm writing that as an exponent. So e to the 13 equals x plus 5. Let's move that 5 to the other side. So e to the 13th minus 5 is equal to x. So we're just plugging that into our calculator. So this one, we just go second natural log. So e to the 13th minus 5, and you should, if you do this right, it's going to be a big number, but it's 442,408.392. So that is going to be 10D. And again, those are all using your calculator. All right, so moving on to 13, we're doing some rationals again here. So this one is going to be solving a rational equation. So there's two methods here. One is to get a proportion, but this one is kind of set up where I probably want to multiply by what would that common denominator would be. So that means I'm multiplying everything, this entire, both sides, by x plus 2, x minus 2, by that least common multiple. So I'm going to distribute that throughout the entire equation. So when I multiply here, the x plus 2's are going to go away. I'm going to get 7 times x minus 2. Here, the x minus 2's are going to cancel when I distribute. So I'm going to get 5 times x plus 2. And here, the x plus 2, x minus 2, they're going to cancel. So you're going to get 10x minus 2. So that's your equation when you multiply by the least common multiple. Distribute here, I have 7x minus 14 plus 5x plus 10 equals 10x minus 2. And now it's just getting the x on one side. So I'm going to combine some like terms. So that's 7 plus 5, so the 12x. Negative 14 plus 10 is minus 4. That equals 10x minus 2. Let's move the 10x over here. Let's add 4 to both sides. That actually comes out kind of nice. So that's going to be 2, and x is 1. Now make sure when you do this, you check for extraneous solutions. 1 is not extraneous because it doesn't make the denominator 0. So we are good. So that's going to be 13a. Next up, we have 13b. I'm going to try the same thing here. I mean, it obviously depends on how this factor goes. But let's go ahead and see. You can kind of tell x minus 6, x minus 2. That's the factor. If you can't tell, test it here. But that's the factor of that right-hand side. So I'm going to do the same method, our strategy I did on A. I'm going to multiply everything by x minus 6 and x minus 2 by that least common multiple. So when you multiply here, the first terms is just going to be x minus 2 times 1, so x minus 2. Here, the x minus 2's cancel, so you have x minus 6. And here, everything cancels, so you just get 4. Now, the biggest difference on this one is you're going to get a quadratic right here. So that's going to change things slightly in how you solve it, but that's x squared minus 6x equals 4. So since it's a quadratic, we need to set it equal to 0. So I will first put the x squared term first. I'm going to combine my x's. So 1x minus 6x is minus 5x. Minus 2 equals 4. So I kind of try to get it in standard form here by combining a few terms and rearranging them. Now I want to set it equal to 0. So that 4 is coming over here. So I have x squared minus 5x minus 6. And now we just factor it. All right, so when you factor, we have x and x. I'm going to try 6 and 1. If you plug in minus 6 and a plus 1, that should work here. Minus 6 plus 1. 3 and 2 does not because the signs wouldn't work with you. But these are going to be your two factors, and these are the two potential answers that you end up with. But we want to check for extraneous solutions. Notice 6 is extraneous. If you plug it in, it's going to give you a 0. So that's going to be extraneous. So your only answer is going to be negative 1. And that's going to be 13b. So 14, last ones here. We are solving some inequalities. So when you solve a polynomial inequality, remember what we have to do on this. These are the ones we use our number lines. So we have to find the zeros, and then we're going to plug those zeros in on a number line. And in this case, I want to see when they're positive. So our answers are going to be written out in set notation. So for A, I'm going to find the zeros. I do that by setting it equal to 0. So I'm subtracting 6x from both sides. So I'm going to get x squared plus 10x plus 24 is greater than 0. And again, I'm going to start by finding the zeros. So that's going to mean I have to factor this and set each factor equal to 0. So that's x, that's going to be 6 and 4, and plus and plus. So if you can tell here, you can kind of notice x equals negative 6, x equals negative 4. Those are my zeros. So I'm going to take those and I'm going to throw these on a number line, and this is where I'm going to test when it's positive and when it's negative. So on your number line, we have the point negative 6 and negative 4. So for polynomials, I like to use that graphing method. You can plot and test points, which I'll have to do over here anyway. But at this point, let's just test our look at our graph. So this is basically a parabola with a positive leading coefficient. So I know based off of this, my graph is going to have this shape to it. So that means it's going to start as a positive. It's going to go through my 0 and become a negative because I don't have any multiplicities here. So it goes through the 0. So if I was kind of sketching it here, it would kind of look like that. And then it's going to be positive again. So I want to know when this graph is positive because I want to know when it's greater than 0. So my answers are going to be, in this case, x equals negative infinity to negative 6. Now we're not including that 0, so we're going to put a parentheses here. And we're skipping all these negative values and going straight to negative 4. And we're going to go off to infinity. So our answer is going to be this. That's when it's positive. So that's going to be 14a. 14b, we already have this factor, but notice this one has some multiplicities that we're going to need to be aware of. So I can jump straight to my number line. I'm just going to write out my zeros. We got negative 8, multiplicity 2. I have x equals negative 5, and I have x equals negative 7, multiplicity 2. So these multiplicities are going to be really important. Also, because you want to look at the degree here, so the degree of this polynomial is going to be all these degrees added up because it's in factored form. So 2 plus 1 plus 2, degree is 5. So this is an odd degree polynomial. Notice all your coefficients are positive, so I know my graph is going to have this general shape to it. So this is my end behavior. So we need to make sure that when we test this, that's the end behavior we end up with. So I'm going to go ahead and set up my number line with all my zeros on it. So my zeros are at negative 8, negative 7, and negative 5. So know that this graph is going to start down on the bottom. So this is going to be negative. So again, I'm starting down here. And it's going to be coming up, and I'm going to touch negative 8. But notice as a multiplicity of 2, which means it bounces. So when you do get up to this point, it's going to bounce, and it's going to stay negative. Then you're going to go to negative 7. Well, notice negative 7, it has a multiplicity of 2 as well. So when you come back up here, it's going to bounce yet again. Notice it's still negative. So I have another negative right here. Next up, I have negative 5. Notice it does not have a multiplicity, so I will go through that point, and it's going to end up going up, and it's going to be positive right there. So my answers, when you look at this, I want to know when it's greater than or equal to 0. Well, remember, that makes these answers actual answers. So those zeros are going to be answers. So when you write your answer out, it's x equals, we have negative 8, and then we have, and if I was doing the set notation, basically it's negative 8 to negative 8. I mean, that's really what it is. And then we have negative 7 to negative 7. And then our final piece is going to be this one right here. Remember, we touched the 0, so we include the 0. So it's going to be from 5 to infinity. So we have negative 8, we have negative 7. Those are my actual zeros. And then I have all these positive values to the right and including negative 5. So those are going to be your 3 sets. These are just basically one number, and that is a range of values. So that's going to be part B. So that's dealing with polynomials. And then the last one that we have, kind of go up here, we have, let's see, orange. Just trying to get my color right. So we have C, which is a rational. So with rationals, there's two things we need to be able to find. So we need to be able to find, in this case, I want the x-intercept, but we also need to find the vertical asymptotes, because the vertical asymptotes are potential places where my function will flip over the x-axis. So I need to find both of these. The difference is the x-intercept touches 0, this one does not. And since we're talking about less than or equal to, we'll have to deal with that. So anyway, before I start, let's go ahead and realize that this is set equal, less than or equal to 3. So when I'm doing this, you want to either, you can set this equal to 0, which is one option that we're probably used to, or you can try to solve it with the 3 in there. I'm going to go ahead and set it equal to 0 because I think that's what we've done the most of. So I'm going to come down here. I'm going to have this set equal to -3 or 0. I'm going to subtract 3 from both sides. So this is going to be x plus 32 over x plus 6 minus 3 over 1 is less than or equal to 0. And especially when we set this up on our number line, that's going to be useful. So I'm going to get a common denominator and combine these. So I'm going to multiply by x plus 6 on top and bottom. So this is going to be x plus 32 minus 3x plus 18 over x plus 6 is less than or equal to 0. So now when I combine these, that's -2x, 32 plus 18, that's 50. So plus 50 over x plus 6, and that is my simplified rational. So to find my x-intercept, first off, my vertical asymptote, that's easy. That's -6. So I got my vertical asymptote. Up here, I'm going to factor this. I'm going to pull out a -2. This is now going to be x minus 25. So your numerator is x minus 25. That makes your x-intercept 25. So this is the one where we really need to test our number line out because it's harder to see that rational, that graph. So when I draw my number line here, we're gonna be testing some points. So I'm going to start with the x-intercept. That's going to be over here at 25. Now what you have to realize when you plot this, I want to be less than or equal to 0. So I'm going to put a closed circle on this because I am going to include that point. Whereas my vertical asymptote at -6, I'm not going to include that point because it's not a 0. That's a turning point, but it's not a 0. So that kind of helps you when you do your final answer, realize you're touching this, but you're not touching this. So from there, I'm going to pick a couple of test points. So I'm going to pick -7, and I'm going to pick obviously 0 in here, and I'll pick 26. And I'm just trying to know when is it positive and when is it negative. So I'm going to take my original equation, not my original, I'll take this one right here, and I'm going to test it 3 different times. I'm going to plug in -7 first, and again, I don't care what the number is, I just care about the sign. So if I plug in -7 into here, -2 times -7, that's positive, so it would be positive plus 50. So I'm going to have a positive divided by -7 plus 6, which is a negative. So this one is going to be negative. Over here, I plug in 0. That's going to give me 50 over 6. That's a positive. So that's a positive for the middle. And finally, when I plug in 26, that's going to be -2 times 26. That's a really big negative. So my numerator is going to be negative as well. Over here, I have 26 plus 6. That's a positive. So I'm going to have a negative. So I have negative, positive, negative. I want to know when it's negative. So my answer is x equals, I'm going to have -infinity all the way to -6. We don't touch it. See that open circle? It's a vertical asymptote. Now I'm skipping over all these values, so I'm going to jump over to 25. I do touch that one, so let me kind of put that bracket in there. So I'm going to go from 25, and actually I want to know when it's negative, so yeah, I'm right. And that's going to go from 25 to infinity. And that is your answer for number, in this case number 14, part C, and that is your exam review.